Hi guys. So the next module is going to be on reverse engineering. So the main purpose of reverse engineering is to take a binary file and to understand what the binary file does and figure out, and the way we do this is by using these reverse engineering applications. So in Pwn College, we've got a few choices. There's like uh, Binary Ninja. There's also Ghidra, Ida. There's also Anger, but I don't know how you start Anger, where it's spelled ANGR. But the one that I'm going to be focusing on is on using Ghidra specifically, because that's the one that I've been using. So first, I'll introduce you to this mystery program. Okay, so our mystery program, it asks us to enter a string, and we can enter a string hello, and we enter a number 10, and it tells us you lose. So how can we make it so that we don't lose then? So that's what we need Ghidra for. So to start up Ghidra, we do GHIDRA and press enter, and they'll take a while to start up. Okay, so first we have to click on File, New Project, and then Non-Shared Project. We will choose our current directory. Of course, this is up to you, but I I personally like to put it in the same directory that I'm working with. So we call it like demo. Okay, so now to start up the reverse engineering application itself, we click on this little dragon looking thing here in green, and this will start up the tool. Okay, and now here we can import file, select our main, which was the file that we were looking at, and we just go through the default settings. Yes, it has not been analyzed. Would you like to analyze it now? Click yes and analyze. And to exit this thing that pops up, just press escape. Okay, so and if we just click on this main, it will make it show up in our decompilation view. But before we go any further, I'd like to introduce a little quality of life change setting that I like to use. So if you go to edit, tool options, listing fields, and then cursor text highlight, by default, it's set to mouse button to activate to middle. If we change this to left and then click OK to apply it. So now if we click on a certain variable, we can highlight all occurrences of it. Normally it's set to the middle mouse button, which I feel is kind of weird and hard to use, so I'd switch it to the left mouse button. Okay, okay, so now we have this main function, and something that might you might find that stands out is that there's these lose and win functions. So what do these functions do? If we double click on them, it will open up the function lose. It says it just prints out you lose. If we click on this arrow at the top here to go back, we can go back and we can check out what win does. Win just says you win. Okay, so now how can we make it so that we win? So if we look one line above, it's checking this ivar3 if it's equal to 0, which is ivar3 is set by the string compare function. So the string compare function is comparing this local 18 plus 4 with the string yes, and it's checking the first 3 bytes. So probably then we have to somehow influence this local 18 variable. And if we look up here, we see that it's set by this get input. So if we double click on get input, so what does this function do? So it prints out enter string, and then it calls gets. This gets is technically not a good function to use because it's unsafe. I'm just using this for demonstration purposes. And then it prints out enter number, and then it calls scanf with this weird DAT thing. If we double click on this, we can see that it's %d. And if you remember how these format strings work, %d means an integer. So we're reading an integer into local underscore 18. And then there's some other stuff. But right now we see, for some reason, we're reading a string into local underscore 18, but also we're reading a integer in, which seems to suggest that we have some kind of structure going on here. So to define our own structure, we can go over here to the data type manager, and if we right click on main, click new or hover over new and then structure, we can define our own structure. And we see that local underscore 18 is 12 bytes. So we can also say the size is 12 bytes. Okay, and again, we saw that it read scanf into an integer in, so we can tell that the first data type here is integer, and we can name this my number or something. And then after that, at local 18 plus 4, we entered a string. And since our local 18 was 12 bytes, uh, and 4 bytes are being used for the integer, the rest is probably the string. So we can call this an 8-byte character array. And we can call this my string. Okay. And to make it more readable, we can call this like a user input or something. And now we save our structure. And now we can change our local 18 variable. So instead of having it be this undefined type, we can change it to our user input type. And so now we get a better understanding of what's going on. So it's setting this AU var starting from byte 0. Or what this means is it starts from byte 0 and it goes on for 4 bytes at index 0. And it sets that to my number. And then after that, it sets the 4th index to my string, 5th to my string index 1, and so on. So this is basically copying over my string into a uvar1. And then also up here, we have that it's setting, starting at index 12 for 4 bytes, it's setting it to this ustack underscore c. Okay, so what is this ustack underscore c? We have this weird concat31 function, which actually doesn't exist in C. This is something that Ghidra is using to help make it more readable for us. To figure out what this actually does specifically, we can go to help, content, and then just search it up, concat. And if we scroll down a bit, we can see concat is a concatenation operator, and it will concatenate the bytes in X with the bytes in Y. X becomes the most significant bytes and Y the least significant bytes in the result. So it's concatenating the second, third, and fourth byte of ustack underscore C with this 0x79. And we right now we don't really know what this 0x79 is for. If we hover over it, we can make an educated guess that it's supposed to represent this character Y. And to change how this is represented, we can right click, and then change it to character. Okay, so now we have an understanding of what's going on here. So we take this AUVAR1 and this AUVAR1 is being returned. So we can call this like full input. And this full input, the first 4 bytes are set to an integer. The next 8 bytes are set to a string, and then finally we have this thing that ends in a Y because of how our cat works. So that means this is probably another structure. So if we right click on main again, click new, click structure, and we see that our full input was 16 bytes, size 16, press enter. So we set this data type to integer. After that, we set it to our 4 byte or 8 byte character array. And then finally, so concat31, like the help describes it, it sets y to the as being the least significant byte. And if we remember how endianness works, uh, the least significant byte will be at the lowest index. So in our structure editor, that means that this y is probably right here at the lowest index. So we change this to a character type. Oops, character type. And we can rename this to y constant. And then for the other names, we can call it the same thing we did before, our number, our string, and then we can rename this structure to full input. And then we save. Okay, so now that we have this, we can change the type of full input to the structure that we just created. Okay, so maybe hopefully this makes our code more readable. So now full input dot r string at index 0 gets set to my string at index 0. So that hopefully this is pretty clear that now it's copying every single index over one by one. Okay, so now we have an idea of what get input does. It asks us to enter a string, asks us to enter a number, and also saves this character y. So now we can go back to our main, and we can, since we know that get input returns the structure that we just created, we can also change the type of this local underscore 18. All input. Okay. So so what happens? We call get input and it sets it to local underscore 18. And now we compare local 18 dot r string to the string yes. And we will look at the 3 bytes. So maybe all we have to do is have it or enter in yes and it'll work, right? If we enter in string yes, yes, and we enter a number, as right now we don't know what this number does, right? Until if you lose. So maybe there's something else that's going on. If we keep reading, we see it's checking if ivar3 equals 0, then we lose. So we actually don't want it to match yes. Okay, but when we made it something that wasn't yes, it also didn't work. So what's going on here? So if we look down even more on line 18, we're looking at, or we take our string and we set at index r number to y constant. So what this is doing, right, is it's setting a certain index of our string to the character y, and then it compares it to yes again. If this time if it matches, we win. So we want a string that starts off not matching yes, but when we put in at a certain index the letter y, it does match yes. So with this in mind, we can use like AES, and if you tell it to replace index 0, we get you in. So yeah, so now we've successfully reverse engineered this main function to understand how it works. Okay, but a few of the challenges in this module also need you to do something else, which is binary patching. So sometimes instead of understanding what the code is doing specifically, we want to change what the code does. So the way we can do this is with binary patching. So let's say instead of having it compare our string with the string yes, or for all 3 bytes, we can make it instead only compare the first 2 bytes. So if we click here, it'll tell us where this line of assembly is. And if you recall, the way that the calling conventions in x64 work is that RDX is used for the third argument. So we can change, if we could change this instead of being 3, it was 2, then we can change how the string compare works. So the way we do this is we right click over here and we click patch instruction, and this will take a little bit to run. And our goal will be to change this 0x3 to 0x2 essentially. Get this rating thing. This is not really relevant. Okay, so instead of 0x3, we change it to 0x2. And now we see that our string compare changed. So now it's comparing with only 2 bytes. And to save this new changed file, we can go to click on File, Export Program. For format, we say original file, and we can call our output file like main2 or something. Okay. And now we can run main2. But actually, we have to change the permissions because it starts off not runnable. If we change it to we can run it. Okay, so if you recall, we changed it so that it's now only comparing the last 2 bytes or the first 2 bytes instead of the first 3 bytes. So now if our starting string has our last character not matching yes, but the first 2 characters do match with yes, then it should pass. So if we enter string yen or something, and then some index, in this case, we no longer care because we don't need to specially switch it out. We can enter like index like 3 or something. And you get you win because now it passed the first check and it also passes the second check, or specifically, if it fails the first check and it passes the second check. Okay. There's also another way we can patch it. So instead of patching like string compare, we can change what functions it calls. So right now, if we fail the second check, it calls lose. But if instead we patch this so that it just calls win instead, so instead of call this address, we call win. Now if we export it, export program, and we call this main3. Okay, so now if we enter random chunk and then some number. Oh, okay. Actually, something else happened here. So we have a segmentation fault. So uh, this segmentation fault you'll learn in more detail about in the module after this one, which is binary exploitation. For now, we'll enter a shorter string, A, B, C, D, E, F, and then our number. And now it prints out you win, because now even if it fails, we still win no matter what. So uh, that's another way that we can patch the file. Okay, so that's it for the reverse engineering part. Here's just a small sneak peek of the module after this. So if we look here, we had this segmentation fault, right? What if we could make it so that instead of like a segmentation fault, we could control it so that specifically we make it win anyways. This might not be clear now, but it will become clear in the binary exploitation module. So we have this payload.txt file, if I echo this file in, now mysteriously this is going to also let us win. You win, and then this segmentation fault core dumped, but we don't really know what that is right now. But yeah, so this is for the module after this one. It's not relevant for reverse engineering right now, but uh, that's it for how to use Ghidra for reverse engineering. Hopefully you find it useful. Even if you're not going to use Ghidra, a lot of the topics that I covered here will be relevant for the other reverse engineering applications. So good luck with your challenges.